Okay, I want to welcome you to another exciting topic on statistics, and you're also welcome to the new month of February. Before I get started today, I want to make some announcement. Number one, of course, you're basically going to see results, your grade for homework one discussion today. That's number one. Number two, the exam practice questions will be published this week. Now, this is what I always do before midterm one, before any exam. I normally release exam practice questions. That will give students opportunity to be able to know, the way the exam is going to go, like in terms of which areas that will be covered. Does that make sense? Okay, so what I always do, of course, I'm actually going to use a class to review the exam practice, practice exam to you. Okay, so we are starting a new topic today, which we call random variables. And of course, this topic will also take us to even next week, where we're going to, talk about this topic further. Now, in the outline, I'm basically going to have a quick review on PGM. I hope you watch the video on PGM. The last lecture that I had, when I got to my office, I, made a video where I extensively explain how you can actually solve problem involving Bayesian network. I hope you watch the video. Of course, the video is already published. If I'm up to date, I've published all recordings. So what I would advise you should do is, go into the video. Now you're going to see in the outline, I'm still going to, review the PGM. Why am I reviewing PGM? Because I really wanted to understand the concept. Okay, that's why I'm repeating that. Then after that, then I'm going to go into the topic of today. That will talk about random variable. Of course, random variable can be discrete or continuous. We're actually going to talk about that. But let's start with this example. On the PGM, on the probabilistic graphical model, of course, the version of the probabilistic graphical model we're working on is Bayesian network. Now take a look at this example. Okay, I'm at work. Neighbor John calls to say my alarm is ringing, but neighbor Mary doesn't call, which means you got two neighbors, right? One call when alarm is ringing, and the other one doesn't call. Sometimes it is set off by minor earthquakes. Is there a burglar? That's a question, right? Now, in the example that we actually want to consider, we got 5 variables. The 5 variables is burglar, earthquake, alarm, John call, then Mary calls. That make it 5 variables. Now, we actually need network topology to represent causal knowledge. Let me tell you this. If you really want to ask, how do we have the structure that we normally have? Of course, we base that on expert knowledge, domain knowledge of the relationship that exists among variables. Okay, so the network topology reflects the causal knowledge. Burglar can set the alarm off, and earthquake can set the alarm off, which means there are 2 things, right? They can actually set the alarm off. Then the alarm can cause Mary to call. Then alarm can cause John also to call. Now, because of that, we have this network. I wanted to take a look at this network. This particular network was actually, given, using domain knowledge, expert knowledge. Okay, now you can actually see the burglary and earthquake, they are the parents, right? Alarm is depending on 2 of them. Okay, and when alarm happens, the next event is either John calls or Mary calls. Does that make sense on how the network is put in place? Any question about that? Okay, now when you take a look at this network that I'm showing now, we have some probabilities associated with each of these network. Of course, it's either there's burglary or not. Okay, is 0.001, the probability that there's going to be burglary is actually 0.0001, which is very, very small. Okay, how did they get that? That is based on past antecedents. Okay, the data set that we normally collect is historical. You know that, right? Based on past antecedents. And of course, the probability of earthquake is actually 0.002. This is given. These are given. The two probability here are prior. They don't depend on anything. But when you take a look at alarm, okay, you know, when you look at burglary, we got two levels in burglary. Why is it two levels? It's either there is that or not. In earthquake, it's either we have the event of earthquake or not. Now, if I now want to condition alarm on burglary and on earthquake, that will be two levels multiplied by two levels. Then what I'm actually going to have, the levels of the alarm is going to be 4. That's why I got 4 levels in the alarm. And that is why you are seeing now in that alarm now, the first one, the probability of an alarm, A represent alarm, given that there is event of burglary and event of earthquake, is 0.95. That occurs 95% of the time. The probability of alarm, given that the event of burglary is true, but the event of earthquake is false, that is 0.94. Now, do you understand the table, right? Do you understand that table? Is there anyone who is struggling with how we put that in place? Okay. When I want to get to John calls now, right? Now we got 2. Don't forget, John called John. J represent John. What is the probability that John called me? Okay, given alarm. If alarm is, given the alarm is true, John called 90% of the time. That's 0.9. Okay, and given alarm is false. The probability that John called given alarm is false is 0.05. The probability that alarm is true given Mary calls, that is 70% of the time, 0.7. And the probability that alarm is false given Mary call is 0.01. Now take a look at this network. What if you're giving this network with a corresponding probability and they ask you this question? Take a look at this question. They ask you the joint, the probability of the joint of all the events. But let me tell you, out of the 5 events, they are talking about negation of the 2 events. Which negation? B and E. If you see that, another way to write, another way to write that symbol of B is to say B complement, right? Another way to write that of E is to say A complement. Okay, so now what they're asking you to do now is, can you find the joint? Can you find the joint probability of J M of J M A B complement A complement? That is what they wanted to find. Any question? That's what they wanted to find. If you basically want to find that, then you're going to make use of the network, the way the network is expressed. Now, how is the network expressed? Let's say, for instance, you don't talk about complement. Okay, even if I'm talking about this guy, if I'm talking about GMAB and he, the way the network is reading, I'm actually going to have the probability of B, the probability of E. Don't forget, starting with that, then I'm going to have the probability of A given what? Given BE, right? Multiplied by probability of J given A, then the probability of N given A. Any question? Any question? This is the way that is what the network expressed. But right now, this is not what I'm interested in, but I'm interested in the complement. The only thing that is just going to change, if I want to put this guy here and put this guy here, then what I'm actually going to do is to come back to where I see BE. Okay, so if you see, you see, you know, I'm talking about this. So the B is going to have complement, even though I'm actually going to have all of it this way: complement, 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 complement. That's all. Take a look at that. Which means I'm still writing the same thing, except that B and E as complement. Is there any question? Okay. Now, if that is taken now, then we're going to be fine. Now we need to go back to the formula. Now, what is the probability of B complement? Oh, the probability of B is 0.001. Then the probability of B complement is going to be 1 minus that. Okay, that was how we got this guy. Any question on how we got you know, the other guy? Let me see. For instance, here now. Okay, let's go back. For instance, here, the probability of B complement will be 1 minus 0.001. Any question with that? Then what about the probability of E complement? That will be 1 minus 0.002. Any question? Okay, now if I want to get this guy now, I will go to the conditional table. What is the probability of A? Given B is false and E is false, because that is the complement. Complement means false, false. What is that probability on the board? That would be 0.001. Let me show you where. Does that make sense? Okay. Those of you online, like the probability of A giving B complement, A complement is going to be this guy, where false, false. That would be 0.01. Okay, so this guy is 0.001. Okay. Now, J giving A. Now, John giving alarm, I'm going to be referring to true. That would be 0.9, right? This guy is 0.9. Then what about Mary giving alarm? That would be 0.7, right? That would be 0.7. And that was what we did here. That was what we did here. If you take a look at that, the probability of E complement is going to, of course, this guy is going to be 0.998. Okay. The probability of B complement, okay, that would be 0.99. That's why you have that 999. Okay. This remains 0.001. Okay. And of course, you can see 0.9, 0.7. You just multiply them. Then that probability, that is the final result. Any question? This can be asked several ways. Maybe in another question, maybe the complement is going to be on this, or you know. So, but the network remain the same. We're going to use domain knowledge. Any question on that? That's going to be the final review on the PGN. So I will advise that you actually work more on that. Okay, now I want to go into today's topic, which we call random variable. Now, let me tell you this. We find ourselves in a world. There's a variation in this world, right? Every, different things happens in different day. Okay, so what do we mean by variable? A variable is anything that is liable to change. Okay, anything that is liable to change. That is what we call variable. Okay, now when we are not talking about random variable now, the random variable is just a way to assign numerical values to element in the sample space. We got a sample space. I told you the other time. The sample space is a collection of possibility, the collection of possible outcome of an experiment. The random variable is a way to assign figures, okay, to sample space. Now we have different kinds of random variable. Okay, we have the discrete, we have the continuous. When you talk about discrete random variable, but then when the random variable can be expressed as a whole number. But we are talking about continuous random variable, then when you can actually have a random variable that lies in an interval. Okay, but let me tell you this: for you to generate random variable, there must be an experiment. Okay, now take a look at this. I said a numerical value to each outcome of a particular experiment, which means they have to be experiments before you start recording values. It's just like in hospital, where the doctor is trying to conduct an experiment to be able to check on the blood pressure of a patient. When you check the blood pressure of a patient in the morning, if you decide to check the blood pressure of the same patient in the afternoon, the result will be different. Okay, so there's always a natural variation that is inherent on any activity. Now, if you take a look at what I'm trying to show you here, okay, it's like I'm trying to say, oh, the particular outcome I got in my experiment from -3 to +3. I'll take a look at that. Now, when you have unknown numbers, you have a discrete one. Now, I'm going to give you an example of how we can actually generate discrete random variables. I told you, variables that can be expressed as whole numbers. They can be expressed okay, the variables that can be expressed as whole numbers. Okay, that's what we mean by discrete. Like the number of students in this class, the numbers of goals scored in a soccer match. That's a discrete. Okay, now let's look at an example now. We basically generate random variable every day, whether from engineering experiment, biological experiment, economic experiment, political experiment, whatever experiment we conduct in this world, we generate numbers. I told you the other time, we need to live this life mathematically because the nature of the world is mathematical. Now, take a look at this. Machine breakdowns. We actually want to define a situation where machine breaks down. Now, if machine breaks down, there's always going to be a reason why it breaks down. Now, the possible numbers of reasons that we can have, that we can attribute to machine breakdown is the breakdown could be due to electrical, it could be due to mechanical, it could be due to misuse. Now, those are reasons, possible reasons in the sample space. Now, when I wrote that in the sample space, I'm trying to tell the world there is no any other reason, okay, that machine can break down except those reasons. Now, if a machine break down, then each of these failure, those are failure, may be associated with your repair costs. Now, let me tell you this: in the past, you've had an experience where machine break down due to electrical issue, due to mechanical issue, due to misuse. Then how much does that cost you on average? You have a record of that. Now that is what we mean by having a state space. The state space now will now be the range of the random variable. Don't forget, the real outcome, is electrical, mechanical, misuse. But every of those reasons, we have a corresponding, repair cost value. Now, on average, when that happened in the past, when machine breakdown due to electrical issue in the past, I spent $50. When it breaks down due to mechanical issue in the past, I spent $200. When it breaks down due to misuse in the past, I spent $350. You can see it in the state space now. We got different values in the state space. The state space reflects reality, where there's always going to be variation, which means you actually spend different amounts, okay, to repair due to different reasons. Any question? Okay, now the cost. Now, if I now want to define a random variable, don't forget, I told you the other time, the random variable is assigning numerical values to elements in the sample space. What are the elements in the sample space? The elements in my sample space are the electrical, the mechanical, and the misuse. Now, assigning random variable to them is like assigning figures to them now, figures like 50, 200, and 350. Any question? Okay. Now, the next thing I actually want to do now, you know, every random variable has a probability distribution. What do we mean by probability distribution? The probability distribution is basically talking about the frequency, like the numbers of time a particular event occur. Because we live in a world where some events has, they have more chance of occurring than others. I'm going to say this again. Some events has, more chance of occurring than others. And because of that, we need a probability distribution. Now, when I'm talking about discrete random variable, the name of the probability distribution for discrete random variable is what we call probability mass function. I'm going to say that again. The name of a random variable for for discrete random variable, the name of the probability distribution for discrete random variable is called probability mass function. Of course, when I start with the continuous one, if I want to talk about probability distribution for continuous random variable, I'm not going to use probability mass function, but I'm going to use a probability density function. It's just like you say, state in the United States, some states are in the Midwest, and while some are in the west, maybe the eastern parts. Does that make sense? That's exactly what we're trying to say. Okay, now, and that was why I said a set of probability value P assigned to each of the value taken by a discrete random variable. What do I mean by that? When an event happens, then it has a probability of occurrence. Every event in life has its corresponding probability of occurring. Now, what does that mean? Now, what is the range of this probability? Oh, it starts to go from 0 to 1. When I had all the probability of the events together, that should give me 1. That's what I mean by summation Pi equal to 1. Then I can now find the probability of an uppercase S equal to a lowercase s equal to Pi. What does that mean? Maybe what is the probability that my repair cost will be $500? There's a probability associated with that. If I really want to know the probability of a repair cost being $50, then it means I need to know how many times in the past does that machine fail due to electrical reason? Because when the machine failed due to electrical reason, I spent $50. Does that make sense? When students, my experience in teaching probability in Africa, Europe, and United States, I realized the student here probability, they're going to say, they're going to be scared. Don't be scared. Probability means the number of occurrence, the frequency of occurrence. That is what it means. Does that make sense? Okay, now take a look at this. Now, what I said the other time. What is the probability? If I now have the knowledge of the frequency of occurrence from the knowledge of the past, what I'm showing you now, 30% of the time, 30% of the time, when the machine breaks down due to electrical reason, I spend $50. 20% of the time when it break down, due to mechanical reason, I spent $200. Okay. And when it breaks down due to misuse, okay, due to misuse, I spent $350. Look at that. 50% of the time. How do I get those probability? That is based on my experience, which means I'm actually going into the past. I actually visited the past. I go into retrospective, okay? And in the end, when I had all those probability together, that give me one, which actually confirm the law of probability. Summing them together has to give one. Now, if I want to generate a plot between the amount that I spend repairing due to machine breakdown to a particular reason, then I can actually make this plot. Okay, what I just did here is just like plotting probability against the random variable. The random variable is the cost, which I'm basically going to go from 50 to 350. And is there anyone who doesn't understand how to generate the plot? Now, why am I generating the plot? I'm generating the plot because I really want to look at the shape. I want to look at the expression. I mean shape. Look at that. I want to look at the shape of the probability distribution of that. Now, you can see in the vertical axis, I put f of s. Okay, this is a lowercase. The lowercase f. In this call, there's a difference between using a lowercase f and an uppercase. They mean different things, which I'm going to tell you now. Take a look at this guy. What I'm doing here is actually different from what I'm doing here. You know what I'm doing here? I'm actually using individual probability. When I'm talking about individual probability now, okay, I'm actually going to be using a lowercase f. But if I want to cumulate, there's something that we call cumulative. So what I want to do now, I want to do cumulative distribution function. In a cumulative, I'm actually going to be using an uppercase f. I'm no longer going to be using a lowercase f. So what do I want to generate here? Maybe in the exam, you are asked to generate a cumulative frequency graph. A cumulative frequency graph is different from frequency graph. The other one where I actually plotted is lowercase f of s against the corresponding, the values of the random variable. That was a frequency plot, but this one is a cumulative one. You know how I'm actually going to do that? I'm going to start from I'm going to start my plotting from the lower value in the state space. The lower value in the state space is 50, right? And what is the probability associated with that? That is 0.3, right? Now, when I go to that of 200, what I'm going to do, if you go back, I'm actually going to add up. I'm going to have a 0.3 to 0.2. That will give you 0.5, which is what I have up to that. Look at the step. Then I'm going to add the 0.5 to the next one, of course. When I had a 0.5 to 5, the last one is going to be 1. What do you see? Oh my God, this is like a step, this is like a staircase, the way it's looking like. And the range of the CDF now is basically going to go from 0 to 1. Do you see that? The 0, even though this is starting from 0.3, but you can see, I'm going to show you now. 0. Take a look at that. So decumulated. Now that is exactly what I'm doing here. This is like how I figure out, the cumulative. Of course, I consider a situation that is greater than minus infinity, but less than 50. That CDF is basically, do I spend less than $50 according to the problem? No. The smallest value that I spend is $50, right? Anything less than 50, that probability does not exist. And that is why it is 0. Do you see that 0? Now, where I now have between 50 but less than 200, okay, that will be 0.3. When I have from 200 to 350 but less than 350, that will be 0.5. Or when I have like, 350 or more, okay, then I'm actually going to have 1. Any question on how this is being derived? Any question? Okay, now the next thing I actually want to do now. Okay, that's all about, the discrete. Okay, now I want to go into the continuous one now. I told you the other time, you got 2 types of random variable. You got a discrete one, you got a continuous one. The difference between the continuous one, let me tell you, in the continuous one, we are, because the variable cannot be expressed as whole number. Of course, the variable is going to lie in an interval. Then you're actually going to need the idea of a calculus here. Okay, the idea of a calculus is required. Okay, now let's take a look at this example. Metal cylinder production. Okay, suppose that the random variable S is a diameter of a randomly chosen cylinder manufactured by the company. And since the random variable can take a value between 49.5 and 50.5, look at that. That is based on experience. Between 49.5 and 50.5, that is not discrete. That's a continuous. And that's why we basically going to call that a continuous random variable. Okay, now let's look at what is the name? What is the name that we call the probability distribution for continuous random variable? It's called probability density function. Let me tell you this. If I want to answer a question that has to do with a random variable, I need to first ask myself, what kind of random variable am I talking about? If it is discrete, then I need a probability mass function. If it is continuous, I need a probability density function. In the future, in this class, we're basically going to be using those functions to answer a question. You're going to answer a statistical, question that has to do with statistical inference. Okay, so for you to be able to, answer the question correctly, that depends on your ability to identify whether you are working with the probability mass function or you are working with the probability density function. But there's something I need you to know. When you are actually working with a discrete random variable, you actually need probability mass function. When you are working with a continuous random variable, you need a probability density function. Now we are working with a probability density function now. Of course, we expect the f of s to be greater or equal to 0. Now, in the case of a discrete, we normally use sum. In the case of a discrete, we use summation, right? But in the case of continuous, we're going to use integral. Look at that. The integral, okay, over the state space is basically going to be the lower endpoint to the upper endpoint. Okay, and f of s ds must be equal to 1. Okay, what this guy is telling me, f of s ds equal to 1 is the same thing as sum of this equal to 1, except that this is for discrete, but this is for continuous. And the name of this guy for discrete is PMF, probability mass function, but the name of this guy is PDF, probability density function. Any question? So far, so good, right? Okay, now, this is the situation. Suppose that the diameter of a metal cylinder has a PDF given as that. Your f of s is given to be 1.5 minus 6 into x minus 50.2 all raised to power 2, and the range is from 49.5 to 50.5. How do we have that function in place? That is according to the expert knowledge. The expert has really looking, they've looked at the way the diameter of of a metal cylinder is generated, that follow that probability function. Now, an f of s equal to 0, you know what that means? F of s equal to 0 means if you are not talking about that range, anything outside the range of 49.5 to 50.5, then the function does not exist. Any question? The function only exists if we're talking about the range of what? 49.5 to 50.5. Any question? Now, what am I trying to do here? That very plot is actually a density plot. The density plot of f of x against x. When I try to use values between 49.5 to 50.5, and I plug in those values in the f of x, and I plot f of x against x, that's what I'm going to have. Any question? That's a density plot. Go ahead. Exactly. It's like you're plugging in the values into the expression. So whatever you have now, it's like you are plotting y, you're plotting y against x. Y in this case is f of x. And the f of x, look at that how. That's exactly what we're doing. Any question? Any other question? So far, so good, right? Okay. Now, what is the next thing we want to do? Do you know we can investigate this guy? Let me tell you this. When you are given an f of x, whether a PDF or a PMF, before you can actually answer question that has to do with inference on that, that f of s has to be valid. Valid. It has to be valid. How do we show that a particular f of s is valid? Because if it is not valid, you know what is going to happen? You're actually going to mislead. Whatever inference, whatever question that you want to use that f of x for, then the result you're going to get will be wrong. Now, how do we show that a given function, because let me tell you something, it is not all functions that are probability functions. I'm going to say that again. Don't forget, you have quadratic function, right? You have a cubic function. We get different kind of functions. But what we need here is a probability function. And how am I actually going to investigate if the kind of function that I have is valid? The only way to know is when I actually integrate that and the result give 1 using the state space. Now that is what I'm trying to do here. You are given a function, right? And you're given the range, right? This is what we, if you remember in your high school, this is what we call definite integral. Definite integral. The definite integral is where you have, the lower endpoint and the upper endpoint. Okay. All what you just need to do is to integrate that. Then you plug in an upper endpoint. Then you plug in the lower endpoint. Then you subtract. The moment the result is 1, what does that mean? Then it means your f of s is a valid PDF. This is a condition for valid PDF. All we just need here is the knowledge of integration. How do you do antiderivative? Any question on this? Take a look at that. Any question? So which means if I give you a function in this class and I give you the state space, I can actually ask you to investigate whether it is a valid PDF. The person online, is that thing still changing for you? The person online, is it still changing for you? I want to see the person online, whether he's hearing me now. Is it still changing for you? I don't think that person is there anymore. You can see the reason why I don't encourage people attending lecture online, because some they're going to pretend as if they're online, and they will just get into the Zoom and they're going to walk away. So the person is not responding anymore. Okay. Now I'm going to go to the next slide. Now, do you know I can answer a probability question? If I use the entire range, okay, if I use the entire range, that should give me 1, right? But what if I decided that I don't want to use the entire range? If I don't want to use the entire range, then what I'm going to get will be less than 1, right? Because I'm talking about the total area under a curve. You know, when I use the entire range, the total area under a curve is going to be equal to 1. But take a look at what I want to do now. We want to find the probability that a metal cylinder has a diameter between 49.8 and 50.1, which means we are not interested in 49.5 to 50.5. We are not interested in the total area under a curve. We are only interested in that blue shaded part. What do you expect to get even before you get the result? The result should be less than 1, because the total area under a curve should be 1. Now, all what I'm just going to do, I'm going to do the same. I'm going to do the same integration, except that what I'm plugging in this time around is going to be different. I'm going to plug in 50.1 and plug in 49.8. And in the end, what do I get? For 0.432. Is 0.432 here? That is expected, because I'm not focusing on the total area under a curve. Any question? So I need you to revisit what you've done in calculus, but it's just going to be a basic one. It's a basic calculus. Okay, now I also want to go into CDF. You know, the other time when we're talking about discrete, we also consider how do we compute cumulative. We also have a way to compute cumulative here. Now, of course, I told you the cumulative has to be an uppercase F. The uppercase F. Now, when I talk about cumulative, what do I mean? You know, for cumulative, I'm actually referring to the probability, okay? The f of x is just going to be the probability of x less or equal to. It means I'm actually terminating at a particular point, less or equal to that. I don't want to go beyond that. That is what we mean. And let me tell you this. That will require that I should integrate my function, the lower case, okay? I'm actually going to go from the lower part. Where am I going to stop? X. Why am I using y? Even though I have x, I have to change it to a different variable. You know why? Because x is going to be my upper point. Does that make sense? So you have to change that. So it means when I integrate this guy, and over this, I'm actually going to get this guy. Then it means if I differentiate this guy, then it should give me that guy. That's what I'm trying to say. F of s, when I differentiate, okay, the CDF, then it's going to give me a PDF. When I integrate PDF, okay, over the range of negative infinity, which is the lower endpoint ever, to x, then I'm actually going to have that. Now, do you know with my CDF, I can actually use that to find the probability of S lie between A and B. And maybe the A and B is a truncated point. It's not the entire range. So what I'm just going to do, you know, I can split the probability of X lie between A and B to. I will start with the upper one, B. The probability of S less or equal to B minus that. And you know what happened? The probability of S less or equal to B is the same thing as uppercase B. What does that mean? If I got my f of x, all what I just need to do is to plug in and plug in A, then I subtract. When I'm doing that, then I'm actually doing the probability of x lie between A and B. And that's exactly what I'm doing. So that is that. And let me tell you this. When you are talking about continuous, Whether you are talking about less or equal, it's the same thing as that. Even if does not have, so they are going to be the same for continue. How many more? Minute, 5 more minutes, right? Oh, thank you so much. Now, you know what I'm trying to do? In the first one, I'm trying to find my CDF, f of x. If I want to find f of x, you know, in the formula, I have negative infinity. I'm not going to use negative infinity. I'm going to use the minimum for that question. What was the minimum? 49.5. Then I'm going to end up in x. Plug in x, plug in that value. You can see the result that I have is in terms of x. 1.5s minus 2 into x minus 50.0 raised to power 3 minus 74.5. How am I going to know that you are right? We have a way to investigate. I'm going to show you next class. Now, if somebody now has to find what is the probability of s lie between 49.7 and 50.0, you know what you're going to do? Your B is the maximum one, 50.0. Your A is a 49.7. All what you just need to do, plug in that value into the f of s, you subtract, you are done. Oh my God, this is super easy. Any question? If you're enjoying this party, this is a statistical party. If you're enjoying my party now, I need your hands up. Oh, you're enjoying the statistical party. But you know what? If you are not enjoying my party, you need to let me know. Okay? You pay for the party. You pay for the service. Okay, you need to let me know. Now, oh, the last page. What am I doing here? I'm plotting the CDF. Okay, I'm plotting the CDF. What is the probability of x less or equal to 49.7? It's going to be, I'm going to go from the lower end point to the 49.7. You can confirm that. That will give you 0.104. What is the probability of s less or equal to 50.5? And what is the probability in between is to subtract them, and that will lead to that. That's exactly what we've just done. Any question? You know what I need you to do? You need to revisit your calculus, because I can decide to give you any function, and I'm just going to be asking this kind of question. So which means you need to revisit. But you know what? I remember when I was in college, there's a way you can verify whether your answer is right before you're going to turn in your document. Okay, so is there any question before I go? I'm going to check again whether the person is here online. Okay, do you have any question? If you are there, I need you to send me a message now. You say yes. Write to me, say yes if you are online. It's no longer online. Okay. Oh, you are online. You're back. Where were you before? Were you not hearing me before? Were you not hearing me before? Oh, you were listening. Okay, good job. Good job for listening. Okay, make sure you stay safe, everyone, and have a very nice day. Bye for now, everyone.